So welcome, folks. This is MonitorSF, local San Francisco-based monitoring group. I'll get in the picture there. I started this close to 2 years ago when I started getting into monitoring at work, and I couldn't find any groups around here. Little beknownst to me at the time, there was actually another group, SF Metrics, that was pretty well established but hadn't been active in a couple months. So for a while we had this group and that group going, two groups. But we've had a hiatus over the past 6 or so months, just because I've been pretty busy with work and stuff like that. But we've got two great speakers tonight here. George talking about monitoring at Stripe, and Nomi talking about pin trace at Pinterest. I want to give a quick 60 seconds to Caleb to talk about Craigslist, because they are graciously hosting this event for us.
Thanks, Brett. I'm Caleb. I've worked at Craigslist for 13 years now, and I'm just shamelessly plugging here. We have open job positions. We always do, but in this particular case, we're looking for system administrators. We're looking for security analysts and programmers of all stripes, in particular programmers that are interested in JavaScript, Perl, Python, React Native. If you're interested in any of this, or know anybody who is looking for work and is interested in any of this, there are job listings on the back there on the windowsill for each of the positions. They're also listed on our site, or you can talk to me afterwards, and I'd be happy to tell you all about what life is like working here.
Cool. And thanks. And I also work for a company called Circonus, who has a time series database called IronDB, who is also helping sponsor the meetup. It's a time series database written in C and assembly, meant for high scalability and performance. And so if you're struggling with like a graphite installation that takes a lot of operator time, or OpenTSDB, or you need several years on your Prometheus install, we just installed or added Prometheus compatibility. Go ahead and grab one of these back there, which tells you about it. And I also have some koozies, because everyone needs to monitor responsibly. And oh, quick show of hands, who's going to Monitorama next week? Quite a few folks. So who here are SREs? I'm not. Developers, sysadmins. Okay, so we got a pretty diverse group, and some of that mixes in with each other. But anyway, let's go ahead and kick it off. I'm going to hand it over to George, who's going to tell us about what Slack is with monitoring.
Hey. So, plug in. First of all, thank you, Fred, for organizing, and thank you, Craigslist, for hosting. To the people, let's see. So to the people who are going to Monorama, I'm sorry. This was kind of like this is the first talk I've ever given, actually. So this was going to be a practice run. So you're going to hear, depending on how this goes, you might hear the same talk or a completely different talk. So we'll see. Hopefully it's the same one, because I really don't have time to go back and do it again. So we're going to talk about Slack and how we started using Prometheus. I'm George. I've been at Slack for about 3 years now, and I'm a visibility infrastructure engineer, and that means that my team is responsible for building, scaling, and operating the metrics, logging, data warehouse infrastructure. And when I first joined, I was just an operations engineer like everyone else there. It was a very small ops team, and we were just struggling to keep everything running, the wheels on. And during that, I kind of just started doing visibility-related things, like helping people out with the logging, and it just kind of turned into a natural progression into what I was doing at Slack full-time. But during that time, I saw a lot of changes in our visibility monitoring systems, and so we're going to talk a little bit about the brief history of monitoring at Slack, why we're replacing the current monitoring we have, and in that, what we're evaluating in a monitoring system, what that looks like today for us, and what the future might hold, and then the lessons I learned while on this journey. So monitoring at Slack, a brief history. Before I get too far into the different systems, I just want to quickly say, as a caveat, that when I'm talking about replacing monitoring systems or any technology in general, I just want to be very careful to not bash anyone, because when you're implementing a tool or employing a tool, you kind of expect it to work in a certain way, and the tool expects to be used in a certain way, and once it's beyond its scale or capabilities, it might not be the right choice anymore, and then it might outlive its function. And that doesn't mean that it's bad inherently. It's just that you're expecting it to do too much. And I think myself personally, I get kind of caught in this trap too, where you say, oh, XYZ software is not good because it doesn't do this, but we never really take a step back and say, like, was it meant to do this? And so I just want to say that in case people who wrote the software that we're replacing, they're not thinking that I'm bashing them because they can write better software than I ever could. So just want to put that out there. So circa 2015 when I joined, this is basically the lay of the land. We were running these logos. I'm sure you recognize most, if not all of these. And it was basically, I don't know what it was like before 2015, but I'm guessing this is pretty much what it was. So we were using Ganglia for host level metrics, Librado for application level metrics via StatsSite, or we're sending it via StatsD, Elasticsearch for logging, and then Isinga for alerts. And at a certain point, maybe towards the tail end of 2015, we started running into some scaling problems with Ganglia. Entire fleets of servers would go missing from monitoring for an unknown amount of time and come back with random host names and unreadable host names. And it was kind of just like a mishmash of scripts to try to keep everything running. And at the same time, we were evaluating Librado and thinking about what we wanted in that. And it looked like we wanted something with that we had more control over. And so we decided to go with something we ran internally instead. So in 2016, we decided to run with Graphite. And for the most part, between these 2 years, these are the main cornerstones of the monitoring stack at Slack. We sent application and host level metrics to Graphite. It was about a 40 node cluster. And then Elasticsearch and Isinga were very pertinent still in our monitoring stack. So why are we replacing Graphite? Well, there were a few things that Graphite didn't really do, our installation of Graphite didn't really do very well for us. From the user experience standpoint, metrics were a little bit difficult to discover, and this also included people who wrote the metric too, because you have to know the exact way the namespacing was set up. And if you didn't, it was hard to click and guess through Grafana, at what point is my metric going to show up. And we actually built a little hack around Grafana itself to pull down a list of metrics from S3 and index that so that people can search the metric, and then it will construct the namespace for you. So that kind of made it easier for people, but it was a combination of not well advertising that and just so many new people joining that the education wasn't being re-upped. So a lot of people, new developers, didn't know where to find their metrics, and that was a problem. Query performance, because of the sheer volume of metrics we're throwing at Graphite, kind of made the rendering of graphs pretty slow. Some graphs would take up to, 45 seconds to load. And as you're sitting there on a dashboard with multiple graphs, it really makes things difficult, especially when you're using it for troubleshooting or debugging a live incident. On top of that, we were doing some kind of silly aggregation on top of aggregations. Due to the same volume of metrics, we were aggregating locally at first using StatsSite and then sending it to our Graphite relay or Carbon relay layer, which then did another aggregation for an AZ. And so then you're starting to get into bad math And a lot of our developers didn't know that. So when they thought they were looking at the 95th percentile or 99th percentile, they weren't getting the right numbers. We're actually giving them an average latency or the max of a latency or something, which is not what they expected, and it wasn't well communicated. And that's just not good for monitoring. And this is kind of a nice to have, but Graphite, at least out of the box, doesn't really support tags and labels. You can kind of build that into Grafana using templating, but then you kind of have to know you're doing it based on the positional spot of the namespace, which is not ideal either. And then from an operational standpoint, we were a team of 6 around the time that Graphite was really handling most of our metrics. And most of those people had joined later on and kind of have never worked with Graphite or didn't really understand our installation. And on top of that, we were responsible for everything else. It was a gigantic Elasticsearch cluster and among other things like keeping Slack up when we had to. Another issue, due to the limited resources, we couldn't really scale the cluster out. And this was a problem when more and more metrics came in. You have an established hash ring, and when you're adding new nodes, you need to recalculate the hash ring, and then under the hood, you need to shuffle metrics around. And we never invested time into building the tools to do that, and so we were scared to scale out horizontally, so we just did it vertically. And at a certain point, that gets very expensive and just not financially responsible. And single node failure. So we're running 2 clusters at a time. So the hot cluster, the primary cluster, and the secondary cluster, they were getting dual written to. But if the primary failed, all the metrics that are hosted on that box would go missing, and this spanned all services. And this was incredible. This is a huge blast radius, and it took some manual failover before we can get the old node up, and then provisioning a new spare took up to a day to do. It was ridiculous. We're also very susceptible to having a developer accidentally just cripple the Graphite cluster. Someone tagging a user ID or a team ID into Graphite would just build so many different metrics that Graphite couldn't handle it. And then on top of that, because the way we did metrics is kind of free to the developer so that they can just log anything or record anything they want. It was really difficult to backtrace it and see who was emitting that bad metric. You had to go through the list of commits or deploys, and then we'd also run the relays in debug mode just to see. It was like a fire hose that you'd have to pick out something that was causing the relays to get overwhelmed. So something clearly had to change on that front, and we had to take a look at what we wanted in a monitoring system before we could replace it. And so, like the previous slides, we're going to talk about the user side and then the operator side. From the user side, of course, you want something to be easily discoverable, the metrics. So if someone is recording something, a counter or some kind of gauge, they want to just be able to type that in and find it without having to go through hoops to figure out when your metric name is going to be recorded. Response time, we wanted that to be much faster, obviously. Custom retention. So some teams wanted some metrics for beyond our predefined retention period, and Graphite just didn't support that for us. And then as Slack is growing, we wanted a monitoring system that could grow with us in kind of the organization. And with more and more servers going in and also the use of ASGs, we're getting a lot of churn in host names, and that can generate more and more metrics, time series as well. And then the metrics, it would be nice if the metrics had some kind of way to slice and dice across dimensions using tags and labels. And then top K queries, it'd be nice if we could quickly find the outliers in some kind of slow API or whatnot. And then also having an API would be nice to be able to query from or build tooling around. And operationally, of course, single node failures cannot cause unacceptable data loss. I think the way the Prometheus is set up, you kind of have to deal with it, but we don't want a single node to crash and then have many, many teams missing metrics and not knowing why. We wanted things to be more isolated, the failure domains to be more isolated. And at Slack, people, the developers in particular, really wanted to be responsible for their own monitoring. And the way that Graphite was set up, it was just a central team handling all, or one team handling all monitoring, which was not scalable. And devs really wanted to roll their sleeves up and understand their systems better and have ownership. And that was very, very helpful for us. So why did we go with Prometheus? Well, for the most part, Prometheus really nails all of these things. There's a couple of exceptions. One is the custom retention period. Prometheus can do that per box, but not necessarily per job. So you kind of have to have another software layer on top of that to kind of handle it. And Thanos, which I'll talk a little bit more about later, is one of those things that looks really interesting. They can do that for you, since they can store your metrics up in S3 and then pull it down to, and then you can just have it there forever. For top K queries, it works in Prometheus. It's done really well because all the metrics are local to the box and they can calculate percentiles and outliers for you. But the way that developers were used to seeing metrics in Graphite, and Grafana for that matter, was different, where Graphite would show you the latest outlier and then graph that time series over the interval, whereas Prometheus would show you each outlier at each step of the interval. So you're getting like tiny little lines here and there that don't really connect. And it's not that it's wrong, it's just for us, when we first saw it, we were kind of shocked by it. But if you understand what it's doing, then it's actually quite nice. And there's actually, I think there's a GitHub issue out to add that feature into Grafana to handle Prometheus's interval. But yeah, Prometheus sounded really good. So what does that look like? What does our installation look like? So now, today, we have 4 softwares we're supporting, with Graphite hopefully transitioning over to Prometheus, and Prometheus getting a stronger foothold in our stack, and perhaps one day we can decommission Graphite, if ever. And this is what our architecture looked like. This is the HA setup that Prometheus developers recommends, just running 2 Prometheus servers that are identical but independent, and in that sense they're scraping the same targets. And Prometheus is a pull method where you actually reach out to the different servers you're monitoring. And we run a primary secondary just to handle failover. But this is it's a very basic setup, and I'm assuming if you're running Prometheus, this is what you're doing as well. And then in the multi-region setup, so if we're running servers from multi-regions, it's not ideal to throw all your metrics around, and it's very costly for a network standpoint. So it's very similar in that we have various single region setups, but the key difference is that we have what we call the hub, where the hubs are just Prometheus servers that solely federate regardless of region. And we do this because we want to be consistent with external labels. So when you're federating from Prometheus, it will tag the metric as with a label called instance or prom or something, where it tells you which Prometheus server it came from. And if you don't federate from all regions, including the region that your hub is in, you're going to get inconsistent labels. And when you're building a dashboard and you're not being consistent, it can be kind of challenging to get the graphs the way you want them to. So we just wanted to be consistent, which is why we're doing that. And you only federate certain metrics that you care about, because if you federate everything, Prometheus just won't be able to handle it. So how we build infrastructure is that we use Terraform. If you don't know what Terraform is, it's kind of like CloudFormation, it's infrastructure as code. And in Terraform, we just specify the module, and you'll provision 2 HA Prometheus servers. We'll configure the Route 53 records for you, which handles the CNAME for Grafana plus the failover. And then it'll configure CloudWatch health metric or health checks, which then will feed into EC2 instance recovery in case the instance fails. Amazon will actually swap out the box for you, just reattaching the EBS to something else, which is nice. And then you can also build optional canaries. So having an optional box that gets spun up with the other pair, but not having all the network stuff configured or all the DNS stuff configured. So you can test upgrades, and you can just hack at the box until you're happy with it, and then test changes, and then you can just decommission it without affecting the primary monitoring. And this is kind of what our Terraform looks like. In the source code, we're just calling some Terraform resources to build your EBS and your the various things in your EC2 instances. But the interesting thing is that in the top level module, you can send a few parameters to configure the box. So here you can send the role and the instance type. Here we're building an X132X large, which is not actually what we're building because that would be, Slack would go bankrupt in a few days. You can configure the volume IOPS, and then you can also configure the volume size. And these are all things that can be configured post-market too, or aftermarket. It's not just the source of truth for us. It's just the way to quickly bootstrap servers. And then job configurations. We're a Chef shop, so all of our configs are managed in Chef to a detriment too. So all of our Prometheus jobs and recording rules are stored in Chef. And this is just how we bootstrap things when things are in prototype. And it's just basically Ruby hash that we convert into YAML, which is what Prometheus accepts. And that leads to a lot of duplicate code for us. So this is something we definitely want to fix in the future, but it works. And then for service discovery, we use the built-in GCE/EC2 service discovery configs. And this basically means that you're relying on the EC2 tags, provider tags in general, just to get a list of instances. And then that will filter down using relabel configs to narrow down the list of instances you want to actually monitor. So let's say, for instance, you're pulling up everything that has a tag. Chef role is MySQL. It's going to look at all the instances, look at the tag, and then give you everything back just filtered on MySQL tag. But this comes at a detriment because one of the AWS representatives had to reach out to us and it's kind of like, you're doing way too many of these describe instances calls, what's going on? And this was maybe a day after we started the Prometheus project. And so it turns out that we were definitely causing at least one of those to be just, this is a global rate limit too, so Amazon can't really bump it up for you. And that was troubling. But they actually both were this is just two servers that was causing Amazon to have real problems. And so this is something we definitely wanted to configure or fix later on. So the main challenge we had with the Prometheus project here was adapting the web app, having the web app send all their metrics over to Prometheus instead of Graphite. And when I say web app, I mean what you think of when you're talking about Slack. It's most of the features, it's all the APIs, it's basically everything. Not the WebSocket stack, but it's just a huge beast, and it emits so many metrics. And just to give you an idea, each web server emits about 70,000 metrics, which comes out to about 35 million metrics based on our pool of servers. And then we're publishing about 79,000 with our job workers, which is our asynchronous queue workers, which comes out to be about 24 million metrics. And on top of that, organizationally, it's one gigantic team that's comprised of many, many teams. And so it's very fluid in the sense that engineers can jump from one team to another, and it's very hard to find ownership over pieces of code, for instance, because that could be someone who worked on that a long time ago. So it's a big challenge. To deal with the volume metrics, we try to follow the best practices for Prometheus as best as possible, and that means that when you're talking about scaling, you need to split off Prometheus by use case, but at a certain point you can't do that anymore. It doesn't make sense to split things up anymore, and so you need to get into sharding. And this is the formula we use for sharding. And on my left side here, you can see that we have some web app collectors that will scrape a subset of servers, and then we federate those metrics back to a hub called Prom Web App, which then we stick into Grafana. And so we also have the Prom node, which is the node, it's using the node exporter, which is the system level, OS level networking stuff. And then Prom default is kind of our catch-all of everything else that doesn't get scraped by those, and then any service that wants their own Prometheus installation, we give them prom foo, and we plug those all into Grafana. And we made surprisingly a lot of progress. When I first started this deck, I was kind of worried because it felt like the project was stalling. And getting everyone to convert over to a new monitoring infrastructure is very challenging. But we actually made a lot of progress. And to give you some context, the team that started transitioning people over to Prometheus is a very small team. We were a team of 3, and the person who had the most technical knowledge about Prometheus was over in Melbourne, and he was like stranded on the island because he was working through his visa stuff. So there was no way for him to come over to the U.S. And so for about a year, we were doing this back and forth, trying to find a couple hours a day to like work with each other and pass work off, but it was increasingly challenging. And so we packed our bags and we went to Australia, and it's very challenging. Like, I wish there was a better story behind that, but we just had to meet in person. And we worked really, really, really hard during that time. We had to meet up with our coworker Tom to try to just sit down and like bang out Prometheus, or at least get some planning and direction. But that's not Tom. That's actually Kiki, and she's a really awesome kangaroo. This is Tom. And Tom is like a really philosophical kind of guy. And one of the main problems when we went over there we wanted to address is, how do we get people to start writing to Prometheus using the web app? And there were a few solutions that were kicking around, and Prometheus actually had a lot of dev support from the beginning. Some of the power users of monitoring really wanted Prometheus because they've used stuff like Borgmon, but the problem is they didn't have time to implement a solution. And so Tom thought long and hard about this, and he came up with a Prometheus library that he wrote himself. And that was I'm very proud of Tom for doing that, because he's not even a PHP developer, but he rolled up his sleeves and did it. And this was actually a big change for us, because now we unblock developers from just using this library and then start to write to Prometheus, and we're starting to see that pick up, which is very exciting. Also, we implemented the statsd exporter. This is the official Prometheus exporter that allows you just to send information from statsd directly to Prometheus using this. But we kind of had to do a little bit different. We had to sample, because we're using statsite, which does some aggregation on its own, we had to samplecate. Samplecator is just like an open source tool that we found that you can kind of duplicate the UDP stream. So one goes to the statsd exporter and the other goes to statsite, where it can still happily go to Graphite. Whereas if you were to use the statsd exporter, the same data gets into Graphite, but we just wanted to build parity there so that people would not feel like they're missing metrics if we just happen to talk about shutting down the Graphite cluster, which I'm not. If you're watching, we're not doing that yet, so don't worry. And then one of our proudest achievements that we didn't even realize that we were doing is that we enrolled 83% of the services on Slack that span multiple regions, and these are things like calls or the WebSocket stack. And the WebSocket stack is what you actually are connected to when you're chatting with each other in Slack. And so that was actually, I'm very proud of the team for doing that. And this is just like a little sample thing I'm showing here, where you can see the graph here. They're the same set of data, but on the left side is powered by Prometheus, and on the right side is powered by Graphite. I'm sure if you're running Graphite, you're probably doing something much better than us, and you're running things, your queries are a lot faster, but this is showing all the users from all regions, and you can see that Prometheus just performs much better, and we actually saw about 2.4x performance increase, which was incredible when you're like actually loading a huge dashboard and you're trying to like troubleshoot a live issue. Oh, I also wanted to insert some proof that people are using Prometheus during live incidents, but as I was searching through Slack, I was like, there's too much stuff to obscure, so I'm not gonna, just take my words, people are using it. So what's next? The future, so this is where we want to take Prometheus next. We want So way too much of our configuration is in Chef, and Chef is not very easy for developers to get their hands on because there's testing is difficult. The way we have our testing pipeline through Chef is difficult. A lot of developers don't use Chef, and they kind of are afraid of just destroying boxes and stuff with it. So we just want Chef to be simple and dumb. We just want Chef to bootstrap a Prometheus server and then let some other function figure out what kind of Prometheus server I am. So if we just pass it some kind of flag or a node attribute, that server can then reach out to something and figure out, oh, I'm supposed to be this Prometheus box. I'm supposed to look at the web app. So then I pull down all my configurations from maybe S3 or something. And that we also want to move the job configs out of Chef. Right now, there's so much duplicate code. It's really inaccessible. So when a developer wants to say, I want to add a job, or I want to modify a job, we're the blockers there, and we want to get ourselves out of the way so that they can do their job better. And in addition to the problem I mentioned earlier about the global rate limits, the service discovery relying on the metadata tags is not always reliable in the sense that whatever your service is that's populating those tags has to be accurate. And for us, sometimes those tags don't get our provisioning service sometimes misses a tag here and there. And if that's the case, sometimes you're missing boxes from your monitoring, which is not ideal. We want something that's better as a source of truth, and right now that's looking like it's going to be console. We have a team dedicated to running console now, and so back when we first started this Prometheus project, that wasn't an option. But now that it's getting a lot of support within Slack, I think we're gonna swap that out and use that instead. Thanos is something I mentioned before. It's a software layer. It's open source. You can throw this on top of Prometheus, and it kind of acts as a management layer. It runs a sidecar on all your Prometheus boxes, and then you can do global queries. And also, it can help you do better HA. It can write your metrics up to S3 and then pull them back down to do aggregations on the spot. And the end goal for this is that we hope that when new surfaces come up, they can just get Prometheus for free. And this is just will isolate any problems with monitoring. Like if a team happens to mess up their monitoring, they don't have to worry about taking out another team's monitoring or whatnot. And this is just something we want in the future. And then finally, the lessons learned. I learned a lot of lessons trying to get this project off the ground. And when I wrote them down, I found that they were just very obvious, probably really obvious to all of you, but it still helped me a lot. Communication is very, very difficult, and it gets exponentially harder when you're talking about doing it across time and space. So working with Melbourne, I don't know if you know the time difference, but like our 3 p.m., 4 p.m. or something is like their 8 a.m., 9 a.m. And during that time, a lot of people schedule meetings with them because it's the only 2-hour blocks that you can have with people in Melbourne. So getting time just talking to Tom was quite challenging. He's a very popular guy. And then also, in addition to that, you lose a couple days in a week because their Sunday, or our Sunday is their Monday, so we're not working that day, and then their Saturday is our Friday. So then, in a sense, you're losing a couple days worth of work. And unfortunately, this is a problem that even for us who are trying to improve communication, I had to fly to freaking Melbourne to like work with Tom and get things off the ground and like really sit down and work with him. So this is something that we're trying to improve, but I think the takeaway here is that just try to be patient when you're working with someone. Try to show a lot of empathy when you're working with someone who's working remotely, because it's tough. It's really tough. For new projects, momentum is a lot more important than getting things done right. There's two sides of this. So the first side is basically it means optimize last, because when you're trying to build something, it's better to get it out first and just iterate and improve on it, rather than the way that, I don't know, when you think about getting things perfect the first time, you might never ship. And I'm sure you've heard this all before. But the second half of that is that if you are leading a project, it's really important to go out and champion and advocate for your team. And that means unblocking them when you can, talking to the right people, getting the right people in the room, just getting things done, and keeping their plates full or empty so they can focus on the task at hand. And the last lesson I can share is demonstrate value early and often. This is important when you're talking about showing things to leadership, and like they might not see the value right away, but if you're demonstrating why it's important to the business, and also to your customers, if you're asking them to replace their monitoring, you need to show them that it's worth it, right? Even if they're excited about it, if they're not seeing the value, how are they supposed to prioritize getting their work done versus helping you, or helping you help them set up the new monitoring, right? Because if something's just working, it might not be worth it for them to change it. So you definitely need to show them some kind of proof of concept or help them along the way. Maybe like something like Tom did where he helped build the library so they can start porting metrics over. Like doing some of that initial legwork helps a lot. And that shows a lot of empathy to your coworkers because they are understandably busy. It's not like they don't want to help, it's just like it's hard to prioritize some work sometimes. And that's it. We're hiring, slack.com/jobs. There's a visibility infrastructure role up there, among others, if you're interested. And thank you for listening to my first talk. This is a worldwide premiere. With a little fanfare, I'm sure. But thank you so much. But,
We do questions.
yeah.
Sure.
How do you use Slack during the Slack?
We have a secret Slack. No, I'm just kidding. We use Google Hangouts, actually. Yeah. We use Google Apps, so it's just like something we crib off of. I think you had a question. Yeah.
So how long did it take you to kind of get this all into production from when you decided the project to getting it in production? And then I guess the second follow-on question, did you look at any proprietary solutions as well as Prometheus?
Yeah. So your first question, how long did it take? Prometheus was kind of like one of the, I joined the project a little bit later, like a few months into it. And it was kind of a prototype that kind of just, I'm sure everyone has this, but it kind of crept into production, and all of a sudden people are using it, and it's like, well, we need to make sure this is actually operable. So I would say it took about a couple quarters, about 6 months to actually get it into production. Confident that it's in production. And to your second question, did we evaluate other things? We did. I didn't do the evaluation, so I don't know the exact reasons why, but we did evaluate other things, and I think Prometheus is just, it had a strong support internally within Slack, and so that's why we decided to roll with it. I think you had a question.
Yeah, I was just curious about on the query composition side of things.
Yeah.
Exploring and modeling and mutating the data that you're looking at, with PromQL is so much different than it is with Graphite.
Right.
What was the story that you had around getting developers muddled up on exploring the data that was recorded? Because now you have so much more data and you can view it in a bunch of different ways. And
Right.
you have all this better provable math behind it, but it's a completely different way of pulling it back out.
Right. That's a really good question. A lot of it has to do with education. So a lot of people aren't really familiar with PromQL, and they're just used to the Graphite way of doing things and using those functions. And a lot of it's just pointing people towards documentation, helping them when possible. I think we still need to figure out a better story around that and getting people more familiar with it. Does that answer your question?
Yeah. And
Okay.
then sort of maybe a complementary question to that is around writing recording rules and how you did your alerting integration. You still had Isengo on there.
Yeah.
I know that Prometheus has like Alert Manager,
Yeah.
its own first-party notification system.
Right.
Did you do an integration back to Isengo, or were you
Yeah.
developers write recording rules and alerts, or how are you handling that?
So Alert Manager is something we don't have in production right now. I think we're going to evaluate it. We are pointing developers towards Grafana alerting for now because it's simpler to set up. But there are people who want to get recording rules set up so they can do recording rules now, but they definitely want to explore Prometheus alerting in the future as well. Yes.
So following the theme of the room, two questions. One being, you said, so you guys are using Grafana mostly, it sounds like.
Yeah.
Do you guys do any management of that, or do you just kind of let the devs do basically whatever they want on Grafana and build whatever dashboards they want?
That's a good question.
And a follow-up to that,
Yeah, yeah. Those are two excellent questions. One, how are we managing Grafana? It's kind of the Wild West right now in there. Like from infrastructure side, we're running, I don't know, like 3 boxes are behind an ASG, so that's able to scale up and down, or not up and down, but we'll replace the box for you if it dies. So from the infrastructure side, it's not really a big deal. From an organizational side, we have yet to explore. I know they released folders recently, which is something we were very excited about, but I don't think we've taken advantage of that fully yet. But yeah, people are able to create any dashboards they want. Right now, I'm actually going through and auditing certain dashboards that are being used, and I think we're going to clean some of those up. This is just part of like a side project while I'm trying to figure out what's the adoption rate for Prometheus and what people are using versus Graphite. And so, yeah, I think, just the basic different roles for each person who signs up for Grafana. I mean, everyone gets enrolled into Grafana when they join Slack if you're in engineering or customer support. But, you can't, like, just delete everyone or anything like that. You have control over your dashboards, and that's basically it. Yes?
2 questions.
Wait, are you serious?
Yeah.
Oh, okay.
There's 2 problems I've seen with Graphite and Grafana over the years are like lack of units. Like there'll be a graph
Yeah.
with no units. And
Right.
it's not inherently part of Grafana.
Right.
How do you enforce that? And then a similar one is how do you know where a metric came from? People can just shoot it at least Graphite.
Yeah.
And quite often you want to track down like where did this number, like what processor, what server sent this?
Yeah.
Do you have any technical or organizational way to?
So the first question, lack of standard units.
Yeah, any units. Like,
Right.
Like milliseconds or seconds, like
Yeah.
I've seen over and over.
Right. I think just from an organizational standpoint, we try to stick to milliseconds.
Oh, do you have a naming convention or something?
Yeah. Well, in our logging or in our metrics library at first, it just kind of standardizes. So if you call it, it's going to be the same units. Versus Prometheus, I think in the best practice, they tell you to use milliseconds, I believe.
But you don't enforce
We don't enforce it. No, we don't. But I think our devs have generally been pretty good about sticking to best practices. Yeah.
And you don't have a way to trace back for a given metric to know.
So you're talking about Graphite, right, in that sense?
Well, yeah, I don't know Prometheus.
Yeah, for Prometheus, it's kind of easy because, like, the team responsible for that service will have that monitoring, so they'll, like, within that team, they'll know, like, who added what to the code.
But then people read.
Right, that's true. But to get to your point about Graphite, to trace back something, we generally have to go, we're just running like the relays in debug mode, and you're kind of just picking out whatever is coming through a lot, or like high cardinality. And we don't have any tooling for that. It's just kind of like using your eyes to eyeball it and then tracing back into code to see where it's being written. So it's kind of like pick and then grep around the code base, the web app code base, yeah. Sorry.
You talked about how there's not like a bad monitoring solution.
Yeah.
That needs to evolve.
Yeah.
Is there any, besides what you talked about with features, that are like a large glaring need that you see in the next couple of years?
Oh, that's a really good question. Glaring need in 2 years. Man, I'm just trying to get everyone over to for Prometheus now. Man.
No, but when that doesn't work out.
Let me think. Next 2 years. I think we want distributed tracing, which is coming up next, which is a nice segue, and structured events coming through. So you can derive metrics, logs, all from the same event rather than like us. We don't have that, so we're sending metrics and logs, and it's like sometimes the same information. So that's definitely something we want to be able to trace a single request through its entire lifespan. I think it's something that we desperately need. Yes, sir.
What's keeping you from getting more off of Graphite?
What's keeping? It's really getting people to commit to doing it. I think devs are just so busy trying to do other stuff, and that's like part of our job is that we should do a better job of showing value and really getting garner more support around it. I think that's the main thing, because a lot of people who are excited about Prometheus and want to get on the ship just don't have the time or resources to do it. But if we can show why it's important and how much better it can be, that can help shape the priorities when it comes to time to goal planning. Yeah.
You said that at the beginning that you had a 40-node graphite cluster.
I think so. Yeah.
How
I think so. I'm pretty sure.
roughly
Yeah.
How many nodes do you currently have dedicated to Prometheus?
We have quite a bit, but they're smaller instances. So because you're monitoring separate services, you don't need to run the same massive, and disk is like not the main thing we're looking for. So I think we're running close to, and because each Prometheus box needs to run two, and we have the hubs and the multi-region stuff, it's close to like, it's around 40, 50 right now. It's probably going to grow more, but like I said, the cost is kind of offset due to varying instance sizes. So some of them are in the edge regions that are not emitting so much data. You can probably run some T2s even, which is quite cheap.
The second part was, so before I joined Craigslist here, I was working in booking. We were evaluating a number of different monitoring systems right before I left. Prometheus wasn't around yet. But the problem we ran into with every single alternative to Graphite was in read load support. So you showed that the read performance is faster with Prometheus.
Yeah.
But we were in an instance where there was a belief that no metric should ever be logged that wasn't monitored in some way. So we had a 5-to-1 read-write ratio on our metrics.
Mm.
So every metric that was written out was read by at least 5
Yeah.
different things. And during an incident, that would go as high as 10x. So
Mm-hmm.
pretty much everyone in the company had access to the Graphite dashboard.
Yeah.
And we were able to get almost everything to scale up on the right side. Influx, TSDB, and I think there were a few others that were around at that point. They all scaled up just fine, but when we switched over even a small percentage of the read traffic, they fell over because they were only meant for dashboards for people and not for automated systems to be actually making business decisions on those metrics.
Right.
Have you tested the read performance on Prometheus, and is that a concern there?
We did. I don't have the numbers offhand, but it performed well under pressure. When it was being prototyped, my colleague Tom did various load testing, and it seemed to be working just fine. I wish I can get you those numbers. I might hit you up later with that. But so far, it hasn't been an issue. I think there's some magic going on with the Prometheus storage engine. It's able to perform quite well. And with Prometheus 2.0 that came out maybe 6 months ago, they were able to reduce their storage footprint by quite a bit too. So disk space was not a huge issue as well. But we did have to tune the IOPS a little bit as we were provisioning servers to figure out what was a good balance. Yes, sir.
Two questions. One is, when you think about the data that you are querying on Prometheus, is it devs looking at their own services? Are there other people who want access to that data? How far into the organization does the data go?
Okay. So I think we have operated under the belief that everyone can look at, if you work at Slack, you should be able to look at the metrics. And for the most part, I think only the devs who work on the services are going to be caring about that. But there are certain dashboards we have that show overall system health and business health. And those we have very diligent people in customer support who are looking at that too and calling out problems ahead of time. And we're like, it's been super helpful. But we don't limit that knowledge to certain groups or anything like that. Did you actually have a second question?
Yeah.
Oh,
The
wow,
second
okay.
question is, has Prometheus as an open source tool, have you been able to take advantage of or fix things or
Yeah.
what's been the
the value is just because we don't have to build it from scratch. And I think this is kind of just how we've always operated Slack, because just put a bunch of tools together and kind of make things work. And when there are issues, yeah, we have committed back to, not Prometheus, but other services such as rsyslog or something, we've committed back to that. That being said, we owe a great debt to the open source community, and we definitely need to be better contributors to that. So hopefully one day when we get more and more people to actually spend time and help us fix things, we can be better about that.
You mentioned earlier something I've been thinking about for a while was being able to correlate, to give different forms of telemetry, use different telemetry systems, log event data, like a time series, metrics, and sort of distributed tracing, in terms of being able to connect those dots. Because it is fundamentally kind of the same data. We're just taking different viewer dimension
Right.
of it. So are you aware of anything or how you would try to tackle the problem of connecting those different
Connecting the dots.
those dots? Yeah.
It really just has to come, like the only way I can think of it working is that if we just derive the telemetry from a single event, because without it, you do have to kind of make some guesses about, did this API call become this request down the line in our job queue, or this notification come from this event. So right now we're just not set up for it, and it's going to take a lot of engineering effort, I think, just to get that sorted out. And then then the doors are open to us. Like I think we'll be in a lot better spot when that happens. But yeah, right now we just don't have the answer. Any other questions? Yeah, thank you so much for listening to me ramble.
You did a couple minutes for kids to refill while everybody sets up. Yeah, straight back. Hey Brad, where's the restroom?
Do you go straight back toward the elevators and then turn right into the elevator? All right.
where could we help from a pocket perspective? Because you're very invested in there's great enthusiasm. So we've tried to take this discussion of not try to compete with, or where can we supplement to help. So,
I'm very I'm a big fan of it. I like your company on this project. It's great.
in the right ways, in the right pockets. And that's the discussion we're trying to do. So, but that's good to hear. We've been chatting and trying to figure out, okay, what is like commodity type metrics that you can put it towards. I guess doesn't need built around. So hence my question on what's keeping you from getting more offer.
We're going to go ahead and kick off the second talk.
Sure. Thank you. Yeah, it's going well.
All right. Thanks, Fred, for setting up this event, and thanks to Craigslist for hosting it, and thanks to everybody else for taking time and attending it. My name is Noman Abbas. I work at Pinterest. I'm on the visibility team there, and I've been there for 2 years, and right now I'm leading the PinTrace project. PinTrace is our distributed tracing system that we've built in-house using some open source components to implement distributed tracing. So here's the agenda for this talk. I'll go over distributed tracing, why we need it, how it's done, and what are some good use cases of using distributed tracing to solve different challenges. Then I'll go over PinTrace, how we implemented distributed tracing inside Pinterest. And then I'll spend some time and I'll go over some tools that we have built in-house and how we use these tools with some examples and real use cases of where these tools were really helpful in solving some of the problems. And then I'll go over some future work. So yeah, distributed tracing. So Pinterest has a microservice architecture like most of the other software companies have now. And in this architecture, we have a number of services that work together to serve user requests. So user request usually comes from client, goes through CDN, then some kind of API service, and then it fans out to backend services. And lots of services that work together to generate a response for that request. It looks kind of straightforward, but in reality, it can get very complex. As companies grow, like in Pinterest case, we have almost 100 services that work together to serve user requests. And we have lots of services. We have complex interaction between services. Because of this, let's say if you're a performance engineer and you want to fine-tune the performance of some user request, it's really hard to see, to find out where the latency is coming from. Similarly, if you're SRE and you see failures in some user requests, how do you know what's the root cause of that failure? And again, if you're just a developer for one of these services, you don't know how that service is interacting with the rest of the services. What are the upstream and downstream dependencies and all these things. So in an environment like this, what do you do? Luckily, we have distributed tracing. So distributed tracing is a tool that we use for monitoring microservice architecture systems. It's very useful in basically understanding how different services are working together. Like this service dependency graph was generated through distributed tracing data. Without this, it's hard to imagine how these services are working together. So you can easily find some logical and architectural bugs in your software stack, which are invisible otherwise or hidden behind some service. It helps you in fine-tuning your performance and finding regressions and operations as well. So all these benefits, we'll look at some use cases for each of these, some example cases, and how we basically use distributed tracing to solve them. I'll quickly go over how distributed tracing works. I'll skip the details, just give some overview because it's kind of involved, but since we don't have time, I'll just give a quick overview. So let's say we have two services, Service 1 and Service 2, and they interact with each other. Service 1 gets a user request. At that point, when it receives a request, it will decide if it wants to sample the request or not. We don't trace 100% of requests because that will be too expensive. We do sampling. Once it decides, okay, I want to trace this request, it's going to create an event, log event called server receive, and it will save that event with a timestamp. Then Service 1 sends a request to Service 2. Both of these services, they'll log events. Service 1 will log client send, Service 2 will log server receive. The response will come back, will log server send, client receive, and then Service 1 will send a response back to user, and we're going to log server send. So once all this information is logged, we can, using this data, we can generate a trace of this one single user request or single transaction. The way we store data is in the form of spans. So one span can be considered a unit of a logical operation where it contains some annotations. In this case, it will contain server receive, server send. That will be one span, this one on the left side. And there will be another span that will contain client send, server receive, server send, client receive. In most cases, one span encapsulates one RPC call, but it doesn't have to be that way. We can have local or in-process spans as well that don't leave the process boundary. Other than these server send, server receive, client send, client receive, we can add some custom annotations as well, timestamp-based annotations, or just any metadata that we want to associate with this span to the request. And each span also has a unique span ID, so that later on you can connect those spans together. If you combine a bunch of spans that are related to a single transaction or user request, it becomes a trace. So a trace will tell you the full story of how a user request is handled by multiple services. In this case, this green section is one trace, and this trace has two spans. One span has just server side information, and one span has both client and server side information. Each trace will have a unique trace ID that we can use to look up those traces and do any kind of analysis on trace data. All right, so pintrace. This is how pintrace architecture looks like. Like I explained earlier, we have clients that send requests through CDN. The request goes to API service, and then all the backend services work together to serve that request. What we have done is we have instrumented all our clients, including iOS, Android, web clients. We have instrumented CDN and most of our backend services such that when a request goes through them, we generate trace data. Once the data is generated, it's pushed to Kafka. From Kafka, we have a Spark job that reads the data, does some kind of processing, some kind of cleanup, those kind of things, and pushes it to Elasticsearch. Elasticsearch is our main data store to store all trace data. From Elasticsearch, we have a number of tools that we use to view this data, analyze this data, do some kind of post-processing or anything else on top of this data. In the rest of the talk, I'm going to go over these tools one by one and show what use cases these tools cover and some examples of where we found them really useful in solving different challenges. So let's start with Zipkin UI. So Zipkin UI is an open source tool built by Open Zipkin community. It's a very handy tool that you can use to view trace data. we store our trace information in Zipkin schema. So for us, it's very convenient to just put this tool in front of our data store, and everything works out of the box. It helps you search and view traces. I'll show you some examples as well. And again, we can use it for various use cases. Here's the UI, Zipkin UI, to search traces. You can specify the service you are interested in, the endpoint or API endpoint you want to look at, and you can give some time, start time, end time, some few more things, and then this will return you a list of traces. Once you click on a trace, this is what you're gonna get. Some of the graphics are not very clear here. We should be seeing some blocks here, but anyways. So this is a view of a single trace, a single transaction or single user request. It's an end-to-end trace where it starts from Android, so our client, and it goes all the way to backend services. So we capture the whole path of this trace. On the top, we can see some summarized data, like what was the total duration of this request, how many services were involved, number of spans, those kind of things. Then on this left side, we see a list of services that work together to serve this request. And in this section, we see some rectangles like this. There should be few above here, but they're not visible on this projector. But these are spans. So the length of this block shows how much time was spent in each of these services. And again, the start is the client send, and the end is the client receive for that span. And again, this trace view gives us a lot of information on how the request was handled by different services. For example, in this case, we can kind of look at where most of the time was spent for this request. Can you guys guess where the time is spent? Actually, it's kind of hard because the top spans are not very clear, but I'll show you guys. Oh, even this doesn't show up. Oh, okay. So basically, this blank area on this side and this blank area on this side, this is the network time, where basically user request starts from client, spends some time between the user and CDN. So a lot of time is spent on network. Then there's this middle portion where some time is spent on CDN. So this is between CDN and our backend services. And then this middle portion is time spent on backend services. So again, from here we can get a clear view of where the long pole is, and if we want to improve user experience, where more energies should be spent in improving the performance. If you click on one of those horizontal lines, the spans, you'll see the detailed information about that span. This will include, again, the client send, server received, server send, client received, annotations, their timestamps, and some metadata, some binary annotations where you can see different things like what was the location of the client, what was the CDN provider, or basically users can add any kind of custom information inside their spans. One more thing that we add to all our spans is standard error logging. So if a service fails on certain request, on certain endpoint, it will log an error inside a span. And it will also log the stack trace for that error, the exception name, and these kind of informations. So all servers will log error, all clients that are sending requests to servers, they will also log error if the request fails. With this, we get a really good picture of where the problem is in a trace. For example, in this case, it looks very different on my screen. But in this case, one of the API requests, v3 home feed, failed, and we can see it's red. Then we can see the failure in downstream services as well. So can you guys guess what's the root cause of this failure? Yeah. So yeah, data service is the lowest most service that had a failure, and that failure kind of trickled up to the next service, and to the API service. So from a trace like this, it's very easy to see what's the root cause. Without this, and again, this is a simpler trace. We have traces where we have literally hundreds of spans. So imagine if there are hundreds of span in a request and there is some failure. Without a tool like this, how would you know where the failure is coming from? And again, these things, I mean, you can do some of these things through metrics or logs, but again, they don't go across service. So you'll have metrics for a single service, logs for a single service. You can add some unique ID for each request and then try to combine them. But this tool does it for you out of the box. Here's another example where we found a kind of a logical error in our code. And the problem, as you guys can guess here, is that we're doing this sequential call between two services. So it's calling the same function again and again sequentially. Once we saw it in the trace, it was very clear that, hey, we need to fix it. We don't need to pay the price of remote calls. We can either send them parallelly in parallel, so that basically all the calls happen at the same time, or we can batch them together into a single call instead of making this step kind of operation. Here's another example. These are spans. Oh, I wish I knew that this would look so bad on projector. I would have changed the colors or something. But let me skip this. Without the colors, it doesn't make much sense. Okay, so next tool is Kibana. Kibana comes with Elasticsearch. And since our data is stored in Elasticsearch, it's very convenient to use it for visualizing our data. Yeah, it's used for visualizing any data that you have in Elasticsearch. It's really helpful in finding trends in your traces. So the earlier tool, Zipkin GUI, is really good in looking at one trace. This tool helps you look at the trends, find outliers or anomalies in your trace data. We can also pull metrics out of your trace data using Kibana, something we were discussing in last session, where basically we have latency information and errors and all those things inside our trace data. So why not just pull it out of the trace data? And it's really helpful in operations since you see the general trend of how things are going. Here's a sample dashboard for one of the services. We can see the QPS coming to that service, the QPS per endpoint, latency percentiles, latency per endpoint, error rates, downstream dependencies, all these things. So it gives you a nice overall picture of your trace data. Here's an example graph where we find the distribution of our client versions. So from trace data, you can figure out what percentage of people are using Android, or iOS or iPad, and within these devices, what versions they're using, because we log this data inside our trace data. And this is just one example. You can pretty much do this for all the annotations that you save inside your trace data. Here's another dashboard. I took a screenshot of a case when there was an incident going on. So there was a bad deployment that happened for one of the services that we have. And on our API layer, we saw a spike of errors. And basically, our users were seeing errors. And from logs and metrics, we could not figure out quick enough that what's the root cause of this error. But from this dashboard, it was very clear that corresponding to this spike of errors in API service, there's a corresponding spike in the errors for Terrapin service. And we also had the corresponding traces. So we just picked the trace IDs from here, put them in Zipkin UI, and saw what's going on. We saw the stack trace. We knew exactly the line of code that was breaking this. And we just reverted that change or rolled back the service, and everything was fine. So with this kind of dashboard, within minutes, we found the problem, and we fixed it. All right, so next tool is Trace Analyzer. This tool helps us do offline analysis and get aggregated view of trace. So the use case for this tool was that it started off with this use case that we would see latency increase week over week or month over month. So slowly the latency would increase for certain endpoint. And the increase will be so gradual that it's hard to tell that at what point, at what deployment, the latency increased. And after a week, let's say there's 10% increase in latency, now there's no way to find out which service or which component caused that increase. So we built this tool, and the goal was to aggregate two sets of traces, one from 1 week ago, one from today, and compare them together and see what's the delta, what's the difference. Here's the architecture of the tool. So we used Jupyter Notebook as a front-end UI from where the user will specify their requirements, what they want to compare. Then we had a Spark job that would pull span data or traces from Elasticsearch and do some analysis, do some aggregation, and push the report back, and then user can see the report in Jupyter Notebook. This is just a UI on how to put the criteria like start time, end time, and endpoints for two sets of traces. Once you trigger that report, this is the outcome. So in the outcome, you'll see for that endpoint, what was the number of traces in that time duration, what was the number of services that were working together at that time, overall latency, calls per trace, these kind of things. In the bottom, we have 3 histograms. The first one is the API service self-latency. So the latency that API service has minus the latency of all downstream services. So it's the latency added by the API service. The last one is the number of calls per trace. So we can see that first and last histograms for batch 1 and batch 2, they kind of overlap. So we see that, okay, there's no problem there. But the overall latency, there's a shift in histogram between batch 1 and batch 2, which means that the overall latency changed, and something in the backend services, some backend service caused that problem. So this tool then tells you the breakdown of self-latency for all backend services, and then it compares them before and after. And then it highlights, oh my God. So basically it kind of highlights, if you can see there's a little bit highlight there. So it highlights which service had the maximum delta in before and after, both in the latency and the number of calls. So there can be a bug in code where now you're making too many calls between services, and that can cause increase in latency as well. So this tool will tell you that, hey, this service is adding that additional latency. And it goes one step further, and even within that service, it will tell you that, okay, this endpoint of that service is what caused this problem. So again, this tool was super helpful in basically finding the root cause of latency increase. All right, so next tool is Python library. So we had all these tools, but then our engineers, mostly performance engineers, they said that, okay, we have so much good data available as part of this trace data. We want to do our custom analysis or our ad hoc analysis, something that basically we want to do once in 3 months or 5 months. So we built this library for them where we provided some helper functions to access the data from Elasticsearch, build the query for them, and simplify the access, and simplify the processing of that data. One example use case of this library was that a team, they wanted to do this analysis that what's the latency difference between cross-zone communication and intra-zone. So we run on AWS, and our services are running on different availability zones. We wanted to see that if we restrict the communication within a single availability zone, will the improvement in latency be worth the effort? And again, with this tool, they just pulled all the data. Trace data has IP address information, so they could easily compute that, okay, these calls are between AZs, and they computed the latency of between AZ calls and intra-AZ calls, and they figured out what they wanted to know. This is also helpful for advanced search. So Zipkin UI, does not let you do a full search on your trace. It does not index all the fields of trace data. So with this, you can kind of download the data on your local machine and then do any kind of search that you want. Here's an example use of this library. Basically, with few lines of code, you can just get the data you want and then do some local analysis. So this again has been really helpful for engineers who wanted to do their custom analysis on the trace data. All right, so what are we working on right now? So now we want to build a continuous post-processing pipeline where we do online analysis. So the analysis that I've been mentioning earlier, same thing, but we do in a continuous fashion where we have the data available all the time, and then we can automate few things on top of it, like we can do automate performance analysis, regression analysis. Let's say you want to compare Canary with prod, so you want to make sure that the new release does not break anything, does not add new latency, does not add new calls to backend services, those kind of things. So, and some advanced visualizations as well. So let me show some examples for this. So here's the architecture of this pipeline. On top, we have the existing pipeline where data from Kafka goes to Spark to Elasticsearch. In this case, we'll create a new service, which will be a post processor and feature extractor. This will read data from Elasticsearch, and it will do some kind of analysis on this data. What should be the analysis? That will be defined by our performance engineer. So we'll make it kind of a plug-in kind of thing where they can define that, okay, this is what we want to look inside the data, so pull this information and store it somewhere. This processor will do that processing, store the information in Elasticsearch, and from there we can view it through Kibana or any other tool that works good for the users. Here's one example of where we are using this tool. Remember in the start, I showed a trace where there was lots of time spent on network and CDN compared to the backend service. Now in this case, we're doing the same analysis. Oh, thank God the colors are showing up. So here we're doing the same analysis, but online. So for all trace data, we're computing how much time. This green part is the backend services, yellow part is CDN, between CDN and backend services, and blue part is the network latency between CDN and user. So we're doing this analysis online. Let's say some incident happens somewhere in any component. We'll see a spike in this in the user perceived latency, and then from this graph, it will be very easy to see what's the source of that spike. So yeah, this will basically help us in automating or alerting on issues that we find in our trace data. Here's another example where we compute the spans per trace. So it shows that basically iPad and iPhone, they have around 400 spans per trace. Android has fewer spans, something to check why there's difference. And then web has even fewer spans. For web, there's a different case. We're not covering all the components, so that might be the reason. But again, this online analysis can tell us that, let's say, again, some release breaks something, and now we're making a lot of network calls for user requests. We'll see a spike of spans here, and then we'll know that, okay, something broke, and we need to go back and take some action. Visceral dashboard. Visceral is a tool that Netflix built and open sourced. It can be used to view the real-time state of your system, of your services. It shows services as nodes and communication between them as links, and you can see basically the data flowing. It's very dynamic kind of UI. You can see data flowing from between services, and there are red dots that show the errors between services. So we did a prototype where using trace data, we can reformat that data and push it to this UI and display the trace information in this graph. This is, again, something very helpful to see the holistic view of your software stack. All right. So in summary, we have 5 tools, kind of. We have Zipkin UI to see a single trace in detail. We have Kibana dashboards to see the trends and pull metrics from your trace. We have Trace Analyzer to do offline analysis. We have Python Client to do ad hoc analysis. And then Post Processor to do online analysis and feature extraction. There's a long list of contributors. This whole project was a cross-team effort. We had people from different teams like service framework, core experience, client side, to basically to instrument different languages, different frameworks. Like we have instrumented Python, we have enabled Java, Node.js, iOS, Android. So basically different members from different teams, they worked on this project to get it working. And that's it. Any questions? Yeah.
How do services take plans actually? So do you ask the developers to use SDK or?
So we instrument our code. We try to instrument the whole framework, like in Python. Our framework is instrumented, so any developer who writes a code will generate traces by default. For Java, we use Finagle, and Finagle has this built-in tracing capability. So yeah, for our developers, they don't have to do anything. It comes by default, and the only thing they can do is add their custom information, like they can add custom spans for something that they want to track, or they can add custom annotations for any information that they want to log as part of the trace. Let's go.
So similar to that, so is that basically kind of similar, are you kind of using open tracing type libraries to generate span, or is this kind of generating log data which you then extract and then extrapolate the spans?
We're mostly using open tracing APIs to implement our instrumentation. And then, we generate the data in Zipkin format. Okay. Yeah. For some services, it's kind of custom, so we haven't instrumented the framework, but we kind of hacked our way around. Yeah.
I'm sorry. I had a similar question was, how did you choose Zipkin as the at-rest schema format? If my understanding is the Zipkin format is a subset of the open tracing schema. Was that a consideration you had, or was that, how did you make that decision?
So that decision was made before I joined. But in general, what I've noticed is that open tracing is more of a API definition and API level details. So yeah, I mean, and then by the time I joined, we were so much invested in Zipkin schema, and it basically we were not running into any issues with that, so we decided that let's keep it. And again, since we use Zipkin UI to view our traces, it made sense to basically stick with it. Otherwise, we'll have to basically rethink what UI we want to use to view our traces. Yeah.
You mentioned, it was probably in the middle of your slide deck, but you had a demonstration of comparing like batches of trace data to understand like where latency
Yes.
kind of started to happen.
Trace Analyzer, yes.
Yeah. Thank you. So for those two batches, I think I missed it, but what's the like? Is this in the case of like a blue-green deployment? Like one batch is like blue, like a blue service that might not have the latest code, and green has the latest code, or is this like what are the batches in that case?
So it can be anything. So in the UI, you can specify time ranges. So it can be week over week.
Okay.
And then you can also specify some annotation. So this binary annotation is, I don't know if you can read, but remember the annotations that I showed within the span? You can specify that, okay, if this span has the country as US versus Canada, compare these two. If it's Android versus iOS, compare these two.
Okay.
So you can specify what you want to compare.
Does that get tricky when you have, like, let's say there is a shared backend service that is used by all platforms, and it's kind of hard to actually understand the latency from that shared service?
Mhm.
Is this, at that point, you're just doing week by week comparisons versus like actual, like in the previous example you just mentioned, like platform differences or even region differences?
So if there's a shared service, depends. Let's pick a use case. Let's say, what do you want to compare? What issue are you trying to solve? Is there higher latencies in one of the endpoints or one of the clients, or depends on what question we want to answer.
Okay.
Based on that question, I think it simplifies the thing. So even if there is a shared service that has a problem,
Mm-hmm.
It will still show up here when you're comparing them.
Okay.
Yeah. Yeah. Let's start from that gentleman here. Yeah.
Maybe the same question I had to the speaker. How are you able to correlate or connect the tracing data to, say, log or event data? Like, say, if you have span, it takes a long time. Are you able to, like, say, have like a link to maybe that event data on in Elasticsearch, and then you can see either the events on either end of that span?
Yeah. So we have some functionality where if we decide to trace a request, we put that trace ID in our logs as well. So when you're looking at a trace, you can search the trace ID in the logs, and it will pull out all the logs with that ID. So that's how we can correlate between connect logs and traces. The only problem is we trace a small percentage, like less than 1%. So if you see a failure in your log, there's a high chance that you won't have a trace ID with it, because logs log everything, traces don't. So it's kind of one way. So it's easy to go from trace to log, but it's hard to go from log to trace. Does that answer your question? For metrics, we don't. It's really hard. Metrics, I mean, we just can't, because it will. If we start adding tags, adding trace IDs in tags, the cardinality of those metrics will just explode. But on the other side, in general, if we're seeing a spike in latency in our metrics, we'll see the similar spike in trace data. Similarly, if we're seeing a spike in errors in your logs, we'll see a similar spike here. So trace kind of is the superset where you'll see if you're seeing some problem in metrics and logs, you'll see that problem in trace as well. The only catch is it's sample. If you are sampling enough percentage of your traffic, then you can actually throw away logs and metrics. Another catch is trace. Right now, we have enabled trace for online requests only. So if you're doing any job, offline job or those kind of things, for them you'll still need logs and metrics. Lots of questions. Let's start from the back. Yeah.
So I think it's you answered some of the questions, apart from the question I was trying to ask. See, about errors, the catch with like, hey, when you're sampling, you could possibly lose a trace that is tracing an error. Do you have any? So my question was going to be like, do you have any different kind of different sampling approach to errors versus regular transactions? Are you doing any adaptability or sort of changing the way you sample based on errors so you can capture more of those errors?
Right now we don't. So it's really hard. Let's say the topmost service decides that we're not going to trace a request, and then some downstream service finds an error. It's really hard to go back in time and start tracing from the start. So right now we can't. Right now it's basically just random sampling. Few things that we do allow is forcing a trace. So let's say a user or a tester or someone sees an error in their usage. Then they can set a flag and say, okay, my next request, I want it to be traced. So they can kind of recreate the same error, and then it will be traced. Similarly, in our integration testing, if some test fails, we then set that flag, enable tracing, run that test, and see the traces and see what's going on. So yeah, we have some kind of custom sampling enabled, but we cannot do on the fly on errors. Yeah.
Yes. So I just had a question to something you just said earlier. So you said if you had enough tracing, you don't really need metrics and logs. Like, what do you mean by that?
So let me show an example. So for example, in this case, if you are tracing requests, let's say in ideal case 100% of your requests, then you can compute QPS from your traces. You can compute latency from your traces. You can compute error rates from your traces. So any metric that you want to compute, you can embed that metric inside your trace data. So even like, don't have an example, but even like these timestamps for client send, actually I have an example. So earlier I showed that we log timestamps for client send and client receive. But in this case, we're also adding timestamp for wire send and wire receive. So these are our custom annotations. So again, let's say you want to add a metric that computes the time right before the packet is sent on the wire. This will be that metric. So does that answer your question? That, I mean, you can embed all that logging and metric information inside your trace. Similarly, this error log. So this is basically just a log statement. So any log that you want to log to your logging system, you can just log inside a span, and it will be there. Yeah.
Obviously, it's still ongoing, but what's the general process to set something up like this?
So I would say pick a standard. Let's say you pick Zipkin or some other standard. Then you need to instrument your frameworks. So it's ideal that you instrument your framework in such a way that developers don't have to do anything. So if they're using some framework, that framework comes with the tracing enabled. Like Finagle in our case for Java, developers, they can just use a template service and build their code, add their code to the service, and their service will have tracing enabled. So instrumentation is one part. Then data gathering is another part, where in our case we use Kafka. Depending on your scale, you can directly push to your data store, or you can use some data pipeline like Kafka. Then you need a data store. You can have MySQL, Cassandra. In our case, we use Elasticsearch. And then some UI to look at your traces. Again, Zipkin has this open source UI. So I would say these are 3 or 4 main components: instrumenting your service, pushing the data to the right place, data store, and then UI and tools that you want to use. And again, Uber has this, I believe it's called Jagger or something. They have this open source project. They have instrumentations available for different frameworks. Even OpenZipkin has instrumentations available for different frameworks. They also provide collectors that you can use to collect data from different services, and then UI.
How long does it take from start to where you are now to get it up and running?
I'm sorry?
To get it up and running, to get this file for you guys to be able to use? 6 months or?
If we have to redo again, then yeah, even 3 months should be 3 to 6 months. Yeah. But this is under the assumption that we tried and failed at different steps and then pick the right path. So over time, we learned that okay, MySQL is not scaling for us, so let's use Elasticsearch, or cannot directly collect data, so let's use Kafka so that we have a buffer. If our collector fails, we don't lose data, these kind of things. Yes?
Here's a new question. So with tracing, you have the ability, give the ability to developers to add custom annotations into that data set. Friday, I think it was, the GDPR went into effect in the EU. So
So when we started this project, from the very start, we decided that, okay, no PII information in this logs. And then again, we had a
Germany considers an IP address to be
So for client IP addresses, we strip off the last part of that IP address to make sure that basically from the trace data, you cannot track back to a single user. So yeah, we keep that in mind. Right now, we don't have an automated way to filter out everything, but we have this thing, we have tools to basically scan our Elasticsearch data to make sure that no one is logging any such information. And again, in company-wide, we have these kind of requirements that, okay, if you're a developer, you should not log any PII information inside your logs or metrics or traces. But yeah, that's something that we want to automate, where basically inside our ingester, we can filter out these things, where if we see something, we kind of trim it right away. Any other question? I think there was one more in the back. Yeah.
I was curious as to what the retention period for tracing data was for you.
Yeah. So we started with 10 days. Now we have 30 days. And we also added a feature. Let me see if there is. Archive feature, this button here. So if you want to save them for forever, you can click this button. This will store your trace to a different backend where we keep it forever. So this is really helpful. Actually, without this, it's really hard to reference a trace. Let's say you find a bug. You want to log a trace in a bug. Without this, if you save the link to the trace, it will go away in 10 days or 30 days. But with this, it will stay there forever. So yeah, it was very useful feature for our engineers.
What's the volume of data that you're looking at for both those time frames?
I'm sorry?
What's the volume of data that you're looking at for both those time frames?
The volume of data, I did not check actually. I don't want to give wrong numbers, but in the end, the limitation was our Elasticsearch cluster size capacity. That's how we define how much data we want to store. And again, the volume actually depends on our sampling rate. So we want to do some smart sampling where, for example, for our canary use case, we want to sample at higher frequency than our prod servers. Similarly, let's say some country has a low amount of traffic. Let's say, I don't know, Brazil has low amount of traffic. We want to sample at high rate for those requests so that we can find problems or trends in those sectors where the request volume is low. So eventually our goal is to scale up and basically trace more requests, but in a smart way. Yes?
How big is your Elasticsearch cluster, and how did you guys go about mapping that out?
So it's a AWS hosted cluster. It has 20 nodes or 22. And again, I don't remember the instance type, but it's one of the big ones. I know it's a relative term, with SSD, so we wanted it to be fast. Yeah. But yeah, big SSDs in 22 hosts.
Do you typically have a team that manage that, like indexers and forkers?
To manage our Elasticsearch cluster, it's AWS hosted, so they do the management for us. It's so far it's doing pretty good. I think in 1 year there was one incident where it kind of started failing, and we had to ping them, and they did something to fix it. But in general, it's pretty stable. Yes.
So you had that list of 12 contributors. How many people do you, so those 12 people were kind of the people who built this to begin with, and then
So out of these 12 people, actually I'm not on that list, so 13 people. I would say 2 are the core developers. So Suman is the one who started this project, and then 1 year ago I took over this project. So 2, you can say, kind of full-time, but again, we were not overlapping. So at a given time, there was 1 full-time developer. But this is for the core pipeline, backend, and the tools that I mentioned. For things like instrumenting iOS or Android, we gave those tasks to the teams that are building iOS app because we don't have expertise on those platforms. So all other developers, they kind of did the part in for their own component. Like some of them are from service framework team who worked on Python and Java tracing, so they made sure that those things are working fine. But yeah, like I said, 1 engineer full-time for the main pipeline to make sure that the pipeline is up and running, all instrumentations are following the standards, and if any developer has any question related to the Zipkin schema or the Zipkin standard or anything else, we can answer those questions, and we can help them review their code and basically make sure they're doing the right thing.
For that standard, did you set that standard? Like, is that something that's evolved with the needs of the business? Like, where did that come from?
So that standard is pretty much, I would say, the Zipkin standard. So we are using standard annotations that Zipkin uses. We are using the standard schema for a span that Zipkin uses. We're using the standard header flags that Zipkin uses to pass information between services to tell them that that tracing is enabled, these kind of things. So yeah, we tried to stick with Zipkin. Any other question? All right. Thank you so much.